14. Are you talking about this one right here? That's the one you were doing earlier, right? You mentioned earlier? Okay. This is a conversion problem. Can I just set it up? I'll quickly set it up and you can do the math. Okay. I need space. So this is page 12, winter 16, number 14. It says we have the density of lead, and that's 11.35 grams per centimeter cubed. We have a block of lead, so this is all lead, and a little piece of this, 1.48% is lead 204. So it's that particular isotope. The rest is other isotopes, okay? So just about 1.5% is that particular isotope. What size of the block in cubic centimeters, so we want to know volume, will contain 8.34 times 10 to the 21 atoms of lead 204. So I want to know how big the block is to have that many atoms right there. Okay? Does the question make sense? The question makes sense? So I want to know how big, what volume of this block would have this many atoms in the shaded spot right there. Okay. This density here that they gave us, though, I believe is just of normal lead. So not necessarily lead 204, just the block itself. Okay? So I've got a little work to do here. And the whole block, you know, is a mixture of different isotopes. Okay, so let's see. I want to know the volume. We've got 8.34 times 10 to the 21 atoms of lead 204. How can I get this to, I want to go to mass. How do I get there? Avogadro's number. 23. This number will be given to you on the exam if you don't have it memorized already. Okay. Now, I would like to go to mass now. Normally, how would you do that? Molar mass. I don't have the molar mass of lead 204 specifically. I have the molar mass on the periodic table of the mixture. The whole thing. Okay. Here we go. We're going to do some advanced 7th grade algebra right here. Okay. This, I want the total mass, right? I want the mass of the whole block. Okay, 1.848% of the block is this. So how do I use 1.48 right now to get to the whole block? Divide by 1.10. I think, did you just say this? Okay, I believe you. Okay, is everybody cool with that? So, it's like an algebra problem. 1.48% of the total is equal to that. So I've got to divide by the 1.48 like I did right there to get the total. Now I can go to grams. Times, what is it, 207.2 grams per mole on the periodic table. And now I can go to volume, because I know it's 11 point, I'm going to use density as a conversion. Okay? Yes? Why can't I use 204 grams? Well, it's not necessarily 204. The only isotope that is exactly is carbon-12, which is exactly 12 grams. But the other ones, it would be around 204, but it might be a little bit off from that. So I don't exactly know what it is. Even if I knew that, that's not necessarily going to get me anywhere. Okay. All right. Cool. Next. Yes? Winter 15. Number 18. Are you talking about this one right here? Part A or B or both? Okay. You're stuck on a particular part or just run through it? Run through it? Okay. So, we've got this 1 molar solution. What amount of stock solution is needed? So this is a dilution type problem. Here. So again, this is Winter 15, page 21, number 18. Okay. So I want... Okay, let's see. I want, from a 1 molar solution, it says, I want to make 100, so this is the stock, that meaning the initial. I want to make 100 milliliters of it, it says. I want to know volume 1. I want to know that initial volume. The problem is, I also don't know molarity 2, or do I? Oh, I do. There it is. I missed it. 0.5 molar. Okay, so that would just divide through by the 1 molar. Cool, that's part A. Part B, what is the concentration of a chloride ion in the stock solution? Well, this is MgCl2. It's basically going to double. There's 2 moles of Cl in every 1 mole of MgCl2. So you double your answer, whatever that is. Okay, next. Yes? Winter 16, number 16. Good, going fast here. I'm trying to go fast so I get as many people as I can. You said number 16? That's a balancing one? Okay. Do you want, were you stuck on a particular part or just run through it all? Okay. Okay. Have you heard of like gaming the test a little bit? Heard those terms? Do you see how that space is really long? And these are short? There's probably a reason for that. Unless I'm just delirious when I write the test, okay? So, we are going to see why that is long and these are short. Okay, this is in terms of variables, I think. Yeah, hopefully you can see them. Okay, so, I would start with the most complicated one. There's how many carbons here?
X.
X. So I put X there. Okay, Y hydrogens here, so what do I put here?
Half what?
Not Y.
Y half.
Over 2, because I'm going to multiply by 2 hydrogens. 2 times Y over 2 is Y. That's not necessarily a fraction, because Y might be 2. So 2 divided by 2 would be 1. So we don't know what the variables are, so we're just going to report them as we get them. Alright, there's WNs here, so I'm going to put WNs there. Alright, now the pain comes for oxygen. Okay, let's just pick a new variable. Who has this question? Oh, nobody. Why am I doing it? Oh, what's your favorite letter? C. Okay. We'll just call it C for now. Okay? So, this is to figure out what the coefficient for oxygen is. This is the last coefficient. Alright, so, Z times 1 plus 2 times C, your favorite letter, is equal to, what's next? 2x plus y over 2 plus 2w. Does a setup make sense, or are there any questions on the setup? So we're solving for C. It's just algebra now. So 2c is 2x plus y over 2 plus 2w minus z. And then c is just that divided by 2. Do you see why this is long now? Because the answer is long.
How did you get 2w?
Well, there's 2 oxygens times w. See the 2 there? Yeah. This is 1 times y over 2. This is 2 times x. This is 1 times Z. This is 2 times C.
Are we only writing it for the oxygens then?
Yeah, because I'm trying to find C. And there's only oxygen here.
Okay.
Is that okay? Yeah. And I've already balanced the carbon, the hydrogen, and the nitrogen. Those were X, Y over 2, and W. Yes?
Can you, well, if you're ready to move on, can we do a problem for net ionic?
Oh, okay. A question on this? Yes.
For any answer, would you accept X plus Y over 4 plus W?
Yes.
Okay.
Yes.
Cool.
Question on this? Okay. Next person. Where did you go? Yes. Net ionic, is that what you said? Do you have one in particular, or does somebody have one they want me to do? Or should I make one up at random?
I don't have one, so.
You don't have one. Does somebody have a net ionic you want me to do?
On that
Same page?
There's one right beneath.
Right below it. Okay, do you want, oh, you get to pick.
Yeah.
Do you want A?
Oh.
So that's aluminum metal reacts with hydrochloric acid. That's a good one. Or B, calcium carbonate reacts. Oh, also a good one. A or B?
B, because my name.
B because of your favorite letter?
Yes.
Yeah, I get that. Okay. Calcium carbonate. So you gotta think calcium, that's Ca2 plus, carbonate is CO3 2 minus, so that's this. Plus nitric acid, that's, well, I don't know why I'm writing it there. That's this. Okay. This is what kind of reaction? Anybody? Double replacement. So calcium will go with nitrate. The nitrate is a 1 minus, so I need 2 of those. And then the H will go to with the CO3. But the CO3 is 2 minus, so I need 2 H's. All right. There's a bunch of stuff that's going to happen right now, but let's just take it one at a time. So the first thing you want to do is write the reaction and balance it. So we wrote the reaction. Let's balance it. 2 nitrates. You're going to put a 2 here. 1 calcium, 1 calcium. 2 nitrates. Oh, we did nitrate already. 2 carbonates. Did I do something crazy here? Oh, it's 1 carbonate. Okay, I was totally crazy right there. Okay, we're good. We're good. It's okay, everybody. All right, next. What was I doing there? Net ionic. So we're doing reaction and balance. Now we want to do state symbols. Better look it up. Get your solubility rules out, which will be on the test. If you have the practice exam reader with you, it's on page 4. Calcium carbonate, wherever you have your solubility rules handy, is what state?
Aqueous.
Not aqueous. It's a solid because of what bullet? The last bullet. Carbonates are insoluble. So that's a carbonate. Okay, next, how about this one? Aqueous, how do you know that?
Acid.
Yeah, it's aqueous acid, you could say that, or bullet 1, nitrates are aqueous, either way. So for the same reason, this is aqueous, nitrates are aqueous. Okay, this is a special one we talked about last class. What happens here?
Water and...
Yeah, this is called a gas-forming reaction. Several compounds undergo gas-forming reactions. This is the only one I taught you because it's by far the most common. This will react to form H2O and CO2. You just have to remember that. That happens whenever you have carbonic acid. So, H2O has what state symbol?
Liquid.
Liquid, and this is?
Gas.
Gas. Those are not from the solubility rules. Those are just standard conditions. All right, I have all my state symbols. Step 3 is to get to the final net ion equation and to get there through electrolytes. So, I've got to figure out what's a good electrolyte. Is this one? No, it's a solid, so neither is the liquid or gas. Only aqueous are possible. How about this one?
Yes.
Yes, but you have to ask, this is what kind of molecule? An acid, and it has to be what kind of acid? Strong. Is this strong?
Yes.
Yes. How do you know it's a strong acid? It's on that table I gave you. Yeah. That's okay, so yes, I'll underline it. How about this one? Yes, how did you know that? It's not from the table. It's aqueous. It's aqueous ionic. All aqueous ionics are going to be good electrolytes or strong electrolytes. So just those two, we're going to write them out as their ions, 2H plus and 2NO3 minus. And this is a calcium 2 plus and a 2NO3 minus. Okay, cancel, cancel. And now we rewrite it nicely. Calcium carbonate, solid, plus 2H plus, aqueous, goes to calcium, 2 plus, aqueous, plus H2O, liquid, plus CO2, gas. Okay. Cool person up there, wherever you went? Okay, next. Yes?
I was wondering about the Roman numerals to the name metals. Does aluminum, you always put
Aluminum, no, aluminum's always going to be 3, so you don't have to do that. How would you know that? I guess because I just told you that. Yeah, that's one of those, people don't, it can be +1 also, but because it's so often +3, people tend not to do aluminum parentheses 3. Yeah, that's just one of those oddball ones. And there's others like that, but I just don't go over them because there's so many. Aluminum's probably one you should know just because it's a pretty common element to see in a molecule. Okay, next I'll go here. You, and then you pair there, and then next, and then you two, and that'll be about it. Yes? Winter 16. Winter 16, that's, we're looking at page 11. Number 11. Is this the one you were talking about? Is that right? Okay. Do you want to kind of run through the whole thing, or did you have a specific question on it? How the heck to start it? Yeah. Okay. This one is one of those that there's the hard way to do it and the easy way. So let's talk through it a little bit. Magnesium has 3 stable isotopes. Magnesium 25 is 10%. What are the percentages of the other 2? The mass of magnesium is that. So I have to move this now to kind of set this one up. The full setup goes like this. Let's see. So there's 3 isotopes of magnesium. Its total is, you'll see, I think I'm writing on the wrong side. Yeah. 20, the total is, in the problem, 24.3050. And this equals the isotopic mass times the percent abundance of each. So for example, the first one is 23.98504, and it's, we don't know its percent abundance, we'll say it's X. Okay, the second one is 24.98584. It's a percent abundance. We also don't know. Let's say it's Y. And then the third one is 25.98259. Its percent abundance finally is given 0. I'm changing it to a fraction 1013. Is the setup okay? Okay, yes?
Isn't the 10% go to the
Huh?
Sorry, that was the 24.985. Isn't that?
Oh, did I put this on the wrong one? Possible. I don't know. Let's see. Let's see. Oh, I see what you're talking about. 25. You're saying this should be with this one? Okay, cool. I'm cool with that. Okay. What is true about x and y and this number right there? Anybody know? Yeah. If they're percentages, they'll sum up to 100. If they're fractions, they add up to 1. Perfect. So now we have two equations, 1, 2, two unknowns, x and y. Solve for x and y. Okay, I'll just kind of leave it at that. All right, second person, you were the second person?
No, could you do that or no?
I don't have time. Yeah, I'll let you do it. It's just algebra, two equations, two unknowns. Yes?
Winter 2017.
Winter 2017. I'd love to do all these. I wish we had a 3-hour review, but you know, stuff happens. What number? 11. So this is page 8. Oh, this is fun. Okay. Carbon, this is from the periodic table. Assuming that you were to pick one atom of carbon. Let's say you had a beaker of carbon. You picked one atom out. And now this number, see it's from the periodic table, it just has one more digit. Okay, what is the chance out of randomness that that one atom you pick has this exact mass? Does anybody know? 0. Why 0? This is the weighted average. So there's carbon 12, for example, carbon 13, carbon 14. You're going to get one of those 3 masses. But you would never get the weighted average mass. That's not possible because it's the average. Is that okay? So there's a probability of 0. Nice one. I really like that question. Just bring it back some year. Okay.
Just last question. Will we go through the oxidation reduction in class?
Yes, tomorrow.
Okay.
Yes. Okay. Last person. Yes.
Winter 2010.
Winter 10. Way rocking it old school here. Hold up a minute. Let me find Winter 10. All 10. Wow, where the heck is this? What number?
21.
21. This is page 63. This is the wine problem I was telling you about. Oh, in office hours. I don't know if you're in office hours. I was talking about this. This is the equivalent problem that is in the reader on, what chapter? Dilution 4. This is on the bottom of page 31. If you want an alternate example, it's the exact same question. A different version of the same question. Okay, this is a dilution sort of problem. However, as mentioned in the reader, because of this one question that's so terrible, when it's complicated, like you keep adding something and add more, etc., really got to go back to the key concept of dilution, which is moles. Meaning the moles are essentially conserved before and after the dilution. So how does that work for this particular question? What happens is, says you are mixing. Oh, there was nobody from Tobadak's class today, but this is his brainchild. I don't know how he came up with this, but it's amazing. X milliliters of wine, that molar. You're gonna mix that with 20 milliliters of wine that is this molarity. So you're mixing these two. The result, this, is mixed again with 30 milliliters of wine. That's this molarity. All of this is going to be, now this wine, which is pretty normal in blending wine, that you mix wines together to get a different taste. So you would mix grapes from different vines. You want to know what's X. Okay, what's the final volume, anybody?
50.
X plus 20 plus 30, or 50 plus X. Okay, so what you're going to do, I'll get a different color. You're going to multiply all of these two numbers. all the pairs you're going to multiply. So for example, this times that, that times that, that times that, and that times that. Is that okay so far? Then you're going to add them. So that times that, plus, literally, plus this times this, plus this times this. That's going to change the multiples, and it's going to equal this times that. Is that kind of okay? There's going to be one unknown, x. Solve for x. Does that kind of make sense? And this is the concept of moles before equal moles after. Multiplying the volume times the molarity, just like we do in M1V1 equals M2V2. It's saying the moles are conserved before and after. Is that kind of all right?
Yeah.
Okay, cool. I'll stop right there. Oh, great question. Do you need to convert to liters? No. How do you all know that? Yeah, you can say for a couple reasons, but because there's milliliters before and after, you don't have to in the same way. You don't have to do that in normal dilution. If you did, there's no loss. All right. Hey, have a great night. I hope the review was helpful, and I'll see you, unfortunately, early tomorrow morning.